Okay, good afternoon. Can you guys hear me?
Yes, Professor. We're hearing clear.
Yes, Professor. Good afternoon.
Great. I don't know if you guys can turn on the camera just for a few minutes. I would like to just to get an opportunity to introduce ourselves, if possible. So I know this is a class for IEs, and I don't think we have any other course in which you see only IE master students. So if you haven't met among you that have introduced yourself, I think that will be a good opportunity for you to introduce yourself today. So I'll start. I'm Dr. Eduardo Perez. I am an associate professor in the Ingram School of Engineering. I'm part of the industrial engineering program. I work with students in my research lab. I am the supervisor right now for Paleanapan and Salvasachi. So I'm gonna be your instructor this semester. I know I couldn't be here last week. So because I was attending a conference, but during this week we're gonna be meeting online, and then next week we're gonna start the face-to-face. I wanted to let you know that I'll continue the hybrid mode for the rest of the semester. So in case you cannot join at some point, you can always connect online using the Zoom. So you saw if you went to Canvas that there are multiple links for the semester. There's a link for each session of the semester, so you'll be able to join via Zoom if you want to. So let's get started. So I don't know if anybody of you wants to go first. Just tell me if you're a new student, if you've been here for a couple of semesters already. I just want to meet you if I haven't met you. And I know some of you I know already, but some of you are new faces. So anybody wants to get started?
I can go first.
Yes, go ahead.
I'm Alexander Little. I'm a second year master's student, so this is actually my last course for the program, with the hopes of defending my thesis in this upcoming summer. I'm currently working in industry as a junior platform engineer, but I might be taking a lecturer position and planning to try to do PhD in the near future. So yeah.
Good. Thank you. Who wants to go next? And Alexander is working with Dr. Sachadon, right?
Oh yeah, I can do the next. And I do research with Dr. Dong too. Yeah, actually this is my second master degree in industrial engineering. And my first master degree is was in New York University in database technologies. And although I come with Dr. Zhu Dong do research just because I want to apply for PhD in the future.
And this is your second semester or first semester?
This is my first semester. Yeah,
First
I just
semester.
joined in Texas State University this spring semester.
Okay, welcome.
Nice to meet you.
Hello, Dr. Fez. I am MD Fantasir Islam, and I'm doing my master's here in industrial engineering. And right now I'm working with Dr. Nova, and my research interest is based on the operation research and my plan to implement like machine learning algorithm in the operation research. And in this course, actually, I'm looking forward to run some manufacturing model in the Arena software. And it's my second semester. That's all. Thank you.
Nice to meet you. Yeah.
I can go next.
Yes.
My name is Catherine Buddy. This is my third semester in the master's program. I'm working with Dr. Jin for kind of the same thing as Fantatcher, just a little different. Machine learning and more so with reliability with wind turbines and that kind of aspect. But yeah, that's about it.
Nice to meet you.
Hello all, I am Palaniappan Subramanian, graduate industrial engineering student. This is my third semester. I'm working under Dr. Eduardo Perez, and I did my undergrad in mechanical engineering.
I think we have Saha. Are you there with us? Yeah, I don't think he's here. Well, it's good. Thank you for joining. No, this is gonna be different, right? We went from online to face-to-face and now go back to online. So hope you guys can hold up. It's a challenging thing to be transitioning back and forward, but see how can we make the best of this semester. Always open to your questions, to listen to your questions. If you have questions, let me know via my email, or you can contact me during my office hours. I'm doing virtual office hours, so you can join via Zoom. The information is listed in the syllabus. Or if you need to see me on a different time, you can also do that. I'm in the English school right now, in the office. I think I like to get the warm up for the semester, so I'm in the building. So today we're going to start with our first lecture, real lecture. We have an introduction already, and this first lecture, as I explained in the introduction, we're doing half and half, theory and modeling. So every week we're going to have a lecture on modeling and one lecture in theory. So today we're going to start with the modeling piece. In the email I sent yesterday, I asked you to try to download the Arena software. So I wanted to know if you were able to do that or not.
Yeah, I think I downloaded the software.
Okay.
It's
Anybody without access to the software?
I'm still waiting for the email for the access, but once that I'm just waiting to receive the download links.
Did you use your Texas State email?
Yes.
I think it went to your spam or junk email.
Okay, I'll check.
Yes, because I did the same thing. And I got the email in my junk email. The reason I asked you, because if you use one of the computers in the English school with Arena, you'll see they might have a version that is older than the current one. If you download the one that is available now for free, it's a limited version, has a limit in the number of blocks that you can use to build software. But for what we're going to be learning in class, that should be enough. But it changes every year. Okay, so this interface changes. So if you're using a different version and you notice that something that I'm showing is not similar to what you're seeing in your screen, don't get scared. It's because maybe the version that you're using is not the latest one. So so that could be something that you will see during the semester. So we'll get started with the lecture. Let me share my screen. So I'll post it, the materials. I'll turn off the video now. You can do the same. So we can. So I call this lab 1, meaning that this is the first lecture on the software. For this class, modeling analysis of manufacturing systems. And I want to get started with the basic terminology that we're going to be using in the modeling component for the class. This information, I'm not asking you to memorize this, but the sooner you get familiar with these concepts, I think the easier it's going to be for you to understand my explanations on Arena and on building these models. So an entity basically is an object of interest in the system. This is what typically you will see moving throughout the system. So if you think about an airport, things that are moving throughout the airport, those are going to be the passengers and the luggage, right? So those could be entities. If you think about a hospital, that could be a patient. If you think about a university, that could be the students, professors, staff. If you think about a manufacturing plant, those are the products that you are producing in the manufacturing plant. So this definition, basically, when I talk about an entity or creating entities, are the object of interest for our model. An attribute is a property of an entity. So this entity can have multiple properties. An attribute is something that is not going to change. Okay, so once you assign that property, unless there's a specific event that you are marking to change that property, if you don't have that event happening in the system, that attribute is never going to change. So for example, you have a box that's your object of interest, and you provide an attribute for that box in terms of a color, and this box is going to be yellow. Okay, so once you assign the yellow color to the box, throughout the simulation, that attribute is not going to change. The box is going to be yellow. Okay, or if you assign an arrival time for the box, let's say the box started to be processed at 10 a.m. and that's the attribute, the arrival time of the entity into the production line. So if you arrive at 10 a.m. and you assign that the arrival time of this box is 10 a.m., that arrival time is not going to change. So if the entity or the box is moving through the process, it's being processed, it's being moved around, every time you call that attribute, is going to be 10 a.m. Okay, so attribute could be a color, a priority, a job type. So the important thing to remember is once you assign that attribute, that is something that is attached to that entity and it's not going to change. A model is an abstract representation of a system. So models can be computer models, or it could be a mathematical model, queuing model. You are familiar with different type of models. The idea of a model is to create an abstract representation of something, so you don't have to work with the actual system, like the real life system. So you don't, for example, you don't stop production, or you don't make changes that are not going to be good for the system. So instead of trying new things into the real system, you're trying those things into a model, and then you get some idea of whether or not those changes are going to be good or bad for the system. So you create this actual representation to make decisions before you implement those changes into the actual system. So that's what we call a model, an actual representation. A system state, a collection of variables that contain all the information necessary to describe the system at any time. So a system state, this is typically associated with the resources that we have available in the system. So for example, if you have a machine, if the machine is processing something, you can say the machine is busy. If the machine is not processing something, then you can say the machine is idle. If the machine is, something happened, it broke down, so you can change the state to failure mode or maintenance mode. This collection of variables representing those different states is what we're going to use to define a state of the system. So for example, if you have a machine that is currently processing something, the machine is busy, and you have another part coming into the machine, by knowing the state of the machine, you can make decisions. Like if the machine is currently busy and another part arrives, then you cannot assign that part into that machine because you have already occupied that machine. So that the decision that the system will make will be different. It will be most likely assigning that part to a different machine or putting that part into a queue. Okay, so those system state variables are going to allow us to understand the actions that are given or the actions that are happening within the system, this discrete event type of simulation. An event is an instantaneous occurrence that changes the state of a system. So an event could be, for example, a machine is idle, an arrival happened, and now the machine is busy. What we call an event is the arrival of the part that is changing the status of the machine from idle to busy. An event list, this could be a set of future events that record of an event to occur now or in the future. So an event list can be, okay, these are the things that we are expecting throughout the day. We expect to have these many passengers showing up at 8 o'clock, at 10 o'clock, at 12 o'clock, at 2 p.m. So that's the expectation that the future list of events that our system is going to be facing. And then the simulation is going to use that list of events to represent the performance of the system in the model. A clock is T-now is a variable. In Arena, it is used as a Arena defined variable that is used to obtain the current time of the simulation. Like for example, if you want to assign an attribute to an entity, the arrival time to an entity, you can use the T-now variable to collect the arrival time for you and assign that to the entity. You assign the T-now variable or the T-now associated attribute to that variable or to that entity. So you can use that information later on in the process. So basically, each simulation experiment will have a simulated time and a clock, a simulated clock, and we can use this current time or T-now to collect the time of an event. So if you want to know what's the arrival time of each entity, you can call T-now every time an entity arrives to a certain point in the model, and that will assign that T-now or that time, current time, to the entity at that point. And then finally, we have a variable. A variable is information representing some system characteristic. So main distinction between a variable and an attribute. And I think that's one of the most important concepts to understand the difference between an attribute and a variable. Again, the attribute is not going to change. The variable can change through the time, through the simulation time. So for example, if you're collecting, I don't know, the revenue, if you are modeling a restaurant, for example, and you're collecting information about how much money are you generating every day, you are going to update this variable every time a customer submit a payment. So if I am a customer, I finish my lunch and I pay, then I'm gonna increase that variable using that amount that the customer paid. So another example could be a working process in the system. So you want to know how many parts are in the system throughout the day. So this is going to be changing during the day, right? So at some point you might have 100 parts waiting to be processed, but later on the day you might have less than that or more than that. And you will be keeping track on that using this variable. So if an entity is arriving into the system, you can increase that. If an entity is leaving, you can decrease that variable by 1. And you know this working process is going to be changing throughout the day given the number of arrivals and the number of departures that are happening throughout the day. So that's an example of a variable. Okay, and those are some of the most important terminology. Any questions about this? Good. So every time we create or we start building a model, I want you to make sure that you save that model before you continue. So once you open the Arena software, make sure that you create a folder and a file, and that you save that file, and that you continuously save that as you continue building the model. Reason I want you to do that is because I have had in last few years students that have built a complete model and they forgot to save at any point, and then at some point the system crashed and they will lose all the information. That could be bad, especially if you are doing the exam. So make sure that you do that from the beginning. You create a folder and then you save the file somewhere. And then as you build your model, you remember to save what you're doing. So in case that you have a malfunction in your computer, you keep the files and you don't lose all the work. So this is an example of how can you, once you set up you open Arena from the start menu, you save the file, your lab directory with the following convention. This will help me in the grading process. I'm going to be doing the grading for this class. So if you help me with the naming of the files, that will be very good for me. You're going to be uploading your work into Canvas. So for the naming, actually, let me show you. So if I go to Arena, you go to File, Save As. I will create a folder here. 320. And then I'll create a, call this lab 1. And then for the naming convention, you can use the lab number, your last name. So in my case, that'll be lab 1 Paris. Okay, and then I'll save it. So when we get into, sorry, this is not. So that's so when I grade, I'll get all of them in the same folder, and then I'll just look at the last name. So that will help me in the grading process. What else? So on the top toolbar, you can select the run. Setup. In here, you can add the project parameters. You can put the title, your name, and then for example here, I'm going to call this lab 1. I'm going to put here my name. And I will uncheck this for now. The statistics collection, if you don't uncheck, that's fine, but I will uncheck because if you leave them all checked, then it will generate a lot of statistics that you might not need for the purpose of the lab. So I uncheck them all, and then when I run the model, I tell the system which statistic I want to collect, so I don't get confused. And then I click apply. And then for the reports, I want you to use the Simon summary report. This is a notepad file that is going to be generated with the results for the system. Okay, click apply. And that's the basic setup. You will get familiar with all this process, and this is why I provide this slide. So if you don't remember at some point, you can refer back to this. The replication parameters are going to change based on the assignment. Okay, so when I say replication parameters, those are here. So how many replications? What is the replication length? What are the base time units? If they are hours, minutes, seconds, all that. So these replication parameters are going to be changed according to the model that you're building. And then there's a batch run here, say no animation. If you want to run your experiment without the animation, you can check that. Or if you want to see the animation, you can uncheck that. The idea is with the animation, it will run a little slow. With the batch run, it will run really fast. Okay, so without any animation. So depending on what you want to do, if you just want to run the experiments, you can click the batch run and it will run really fast. Or if you are just focusing on building the animation, making sure that your model is doing what it's supposed to do, then you can uncheck this and you will see the animation. But the simulation itself is gonna run kind of slow. Okay, so that's in terms of the setup. Now I want you to get some idea in terms of the modules that we are gonna be using to begin with. So the way I teach how to use Arena might be, I mean, some of you might have some experience, especially those of you who were here for your undergraduate degree. But the way I teach Arena, I start with the basic blocks first, so you understand the logic behind the current interface. I also like to teach the basic blocks because they offer more flexibility in terms of building a model. Since as we move, let's say the past 15 years, Arena have combined many of the original blocks into a single block. And when they do that, they make them easier for the user, but at the same time, they lose flexibility in terms of the type of models that they can create. So I like to teach the basic blocks just in case in the future, if you need to use Arena and you are requested or you need to build a logic that is challenging, you might not be able to find the blocks in the current templates. You might need to refer to the list of blocks that were originally designed with Arena. Okay, so you'll see what I meant in what I mean in a few minutes. So the Arena modules, we're gonna use the blocks and elements templates. And we're gonna start looking at the elements. Okay, so elements are the blocks that are used to create your experiments. Okay, so this is a separate, in our model, we're gonna have a experimental module, and we're gonna have a, we'll say experimental module and the model. Okay, so in the experimental part of the model, we're gonna have the elements. And we're gonna start with the resources elements. They define the characteristics of the resources, including the resources names and initial capacities. Capacity represents the number of identical units of resource name that are available. So the idea is, if you have a station that has multiple identical machines, that you don't have to build a machine model for each one of those machines. You can just build one and change the capacity because they are identical. So by just building one of them and increasing the capacity, let's say you have 5 identical machines, you can say you can build only one model for the machine, and you can say, using that model, I have 5 of those. Okay, and that only works if the machines are identical in terms of processing capacity and so on. Okay, so in the resources element, you can change the capacity for the station if you have identical machines. You are also creating the names for the resources and so on. And then once you define the element or the experimental piece for the resources, in the model itself, you're gonna have a group of blocks that are going to be used to model a resource. The first one of those models is called the sys block, and uses a resource and remove it from the list of available resources, basically saying, okay, an entity has arrived. It needs to be processed. So I'm going to use this sys block to find out if there's any resource available that can process this machine. That's basically what the sys block is doing. So for example, a carpenter uses a hammer. The hammer is no longer available until the carpenter is finished with it. So the sys block is gonna let you know there's a machine or resource available. If there's no resource available, then you're gonna have to wait. I'm gonna keep you waiting. But if as soon as one of them becomes available, I'm gonna pass you to that resource. Then that's the first block. The second block is the delay. This represents a delay caused by some factor. So for example, a worker goes on a break for 30 minutes, then that means you have 30-minute delay in the process. These also represent, like, if you find a resource available and you know how long it takes for the part to be processed in that resource, then you can use a delay to model that time. So the sys is gonna let the entity move to the delay. Delay is gonna hold that part for this amount of time, which is modeling the processing. And then once that time is completed, the delay block is going to release that entity. And typically that block is going to be connected to a release block. So once the entity leaves the delay block, it's going to be transferred to this release block. The release block, what it's going to do is to release the resource that is being used or was used by the entity. So it will return a resource to the resource pool. So for example, a carpenter has finished using the hammer and it returns it to the toolbox. So those 3 blocks, the sys, delay, and release, are going to be used to represent the resource in the model. In terms of statistics, for today, we're going to learn how to use the counters. This is typically used to count, very simple, how many entities are crossing a specific area of the model. But in order to define a counter or a count, you have to use a counters element. So the counters element specify parameters for counters that may be used to keep integer count statistics for events occurring in the model. So in the elements, you will define the name of the counter and the increments of the counter. So if you are going to increase every time someone crosses this block, if you're going to increase it by 1 unit, 2 units, 3 units, and so on. The count block increments the count is specified by counter ID by the value of the operand counter increment. So for example, number of units completed, that can be, you can compute that using a counter. Okay, so to complete today's lecture, we're going to be working on building our first model. This first model is going to have just a single machine, and it's going to have a set of parts, the entities arriving following a probability distribution, and they're going to be added to a queue. They'll be waiting in the queue to be processed by a machine. The processing time of the machine is also given by a probability distribution, which is a triangular 3.2, 4.2, 5.2 minutes. And then after they're processed, they're going to be counted. How many parts were completed? And the question that we are trying to answer is how many units are produced in 8 hours? Okay, so that's the model that I want you to work with me today.
Professor, what is the triangular processing time 3.2?
That's a probability distribution, and triangular is one is the name. Triangular is the name of a probability distribution that has 3 parameters: a mean, I think it's mode, and the max. Okay, and the shapes is something like this. So you have a minimum value, a maximum value, and the mode. And this triangular distribution is used to represent the processing time for the machine. So for example, what this is telling us is that most likely it's going to take 4.2 minutes to complete the part, but there's some variability associated with that. Sometimes it will take less than that. Sometimes it will take more time. So what the model is going to do, every time a part arrives to a machine, the simulation model is going to generate a random number based on this probability distribution, and is going to assign that to the processing time. So for example, a number that can be generated by this triangular distribution could be 4.0, because it's a number that is between 3.2 and 4.0. So the next entity is going to take 4 minutes to process into this machine. These probability distributions, right now I'm giving you that information. Okay, I'm telling you this machine processing time follows a triangular distribution, and same thing for the interarrival times. I'm telling you the interarrival times follows an exponential distribution. But typically, or basically, what I'm saying is these are probability distributions that you have to fit from real data. Okay, so, and that's going to be part of your project for this class. As part of the project, you are going to be analyzing a simple system, and you're going to be collecting data from that simple system. Could be a restaurant line, fast food restaurant line, or a bank line. Very simple system, but you're going to be collecting data on how long does it take to serve every customer, and how often you get arrivals into the system. And part of the project is going to be for you to determine these probability distributions. So you will learn how to get the probability distributions this semester. But for now, I'm telling you, these are the probability distributions and these are given, but those are generated using real data from the system. So you will go, you will collect the processing times for this machine throughout the day. And at the end of the day, you will have 200 data points. So you will use those 200 data points to try to fit the probability distribution, try to fit the best probability distribution that follows the uncertainty given by that machine. Does that make sense? Saha?
Yeah, Professor. I understand the triangular
Okay,
distribution.
good. So let's try to build this model. Okay, so let me get started by just showing you, if you downloaded the latest version of Arena, this is what you're gonna see once you open Arena in your computer. You have a project bar that has a group of templates, right? So you have data definition, script processing, decisions, grouping, input, output, animation, excuse me, material handling. For now, we are going to ignore these templates and we're gonna add the templates that we just discussed. So in order for us to get those templates, we have to put our pointer or the arrow on top of the template and do a right click. And then select template panel, attach. And that should take you to this folder. Let me know if you're seeing this same folder in your computer, if you're not seeing it. If you're seeing it, you're good. If you don't see it, let me know. Okay, so we're gonna select the blocks. So click on the blocks and hit open. And then we're gonna do the same thing. Right click, template panel, attach. And we're gonna select the elements. And now the templates that we are going to be using are the blocks and the elements. As you can see from this list, it's a very long list, gives you a lot of flexibility. Same thing here, very long list. Okay, so any questions so far? Make sure that you save. So save as that one. Paris, very good. So I'm going to start by defining my experimental frame. So I'm gonna go here. See here. I'm gonna add some text here just to illustrate experimental frame. These are going to use the elements. And then I'm going to add another This is the model frame. Here we're gonna use the blocks. Okay, so we're gonna start by defining our experimental frame first. And we're gonna be using the elements for that. Okay, so in this model, we have a machine, and we're gonna be counting, right? And we will need a queue. So in my experimental frame, I'm going to be adding those three things. I'm going to start by adding the queues, because my system is going to need some queues. Or one queue, actually. Remember that we're using the elements. If you go to blocks, you can find queue. But that's not the block that I'm using. I'm using the elements to define my experimental frame. So I need to go to elements and select queues. Okay, I'm going to also, from the elements module, select resources. And from the elements modules, I'm going to select counters. Any questions so far? Okay, so if I double click on the queues for this system, I'm going to need a queue in front of the machine. Okay, so I'm going to create that queue. When you open, let me go back here. When you double click this, you will have this window. We're going to add a queue in our system. And that shaded area, it is what's required for you to input in order to use this block. Okay, so in this case, the only thing that is required is the name. So what I'm going to do is to change this name to machine queue. And I'm going to click OK. If you want to edit that, you can just click on top of it, click edit. The other option that you have here is the selection type of queue that you're gonna run. We're gonna follow the typical one, first in, first out, but you have the option of changing that depending on the type of queue. FIFO is the same as first in, first out. FIFO is first in, first out. LIFO is last in, first out. And low value first and high value first. So these four are the same as these four. So first in, first out. And then in my model, I have a single machine. So I'm going to add, again, the name of the machine. I'm gonna call this machine 1. Remember that the shaded portion is the only thing that is required. So I'm using name convention, machine 1. You can change the capacity as we mentioned. If you have multiple identical machines, let's say instead of having one, I have 3 identical machines. I can just say, okay, I'm gonna have 3. We have a capacity of 3, but that's not the case. You're just gonna have 1, so capacity 1, and then click OK. Let me go back here. I don't like to use capital letters unless they are in the middle. So scene 1. It's not letting me fix it. Okay, it's not letting me change it. And then in the counters, I'm gonna have one counter. I'm gonna call these parts completed. My naming convention is I don't leave space in between. Arena is gonna throw you an error if you don't use the same characters. So it's case sensitive. So for me to make sure that I don't make mistakes, I try to avoid the spaces. So instead of using spacing, I use a capital letter when I start a different word. Just like I did here, parts completed. Okay, so I have defined my experimental frame. These are the 3 things that are going to be part of my model. These are the 3 things that I'm gonna use for my experiments. Now I can build my model. Any questions? So let's go to the blocks. We're gonna start by creating some entities. So I'm gonna use the create block. The create block is used for creating entities. So if you click here, we can define the time between arrivals. Like for example, if I want an entity to arrive every 5 minutes, I can tell the model 5. So every 5 minutes, an entity is going to arrive. If I want an entity to arrive every 2 minutes, then I can put a 2 here, and every 2 minutes, one entity is going to arrive in the system. However, since we are using simulation modeling, what we are trying to do is to address the uncertainty in the system. If we knew for sure how often the parts would arrive, if we know for sure that parts are going to arrive every 2 minutes, and it's going to take only 5 minutes to processing them, if there's no uncertainty in the system, there's no need for us to use simulation. We can solve those problems using queuing. But since we know that there's uncertainty in the arrivals, in the processing time, and so on, that's why we are using simulation, because we cannot solve those type of models by hand or using equations. We need computer models to help us understand the impact of the uncertainty in the system. And that's why we are using probabilities distributions to represent the inter-arrival times and also the processing times in the machines. So as defined here, these inter-arrival times are going to be modeled using an exponential distribution, 4.4. So the way ARENA works, if you want to define a probability distribution, you can build an expression. You can look at random distributions, and you can define an exponential 4.4. So ARENA, what it does is you use the first 4 letters of the distribution and put into parentheses the parameters for the distribution. So you can write it by hand, or you can create it using the expression building. So let me show you that one more time. If I go here, if I right click I can build an expression. I choose a random distribution, exponential, with a mean of 4.4. And then I click OK. So I'm going to be creating these entities every more or less 4.4 minutes. Could be 3, could be 5. The model is going to be generating these events using that probability distribution. And then you're going to move these entities that you're creating to a queue. Okay, so I'm going to connect these two. I want to connect them. There's an icon or a button here at the top. You go to the Home tab, click there. You can connect these two blocks. And then you can double click. It is asking you for the queue ID. Since we already defined the name for the queues here in the experimental frame, we can just click here and select the machine queue that we define in the experimental frame. And that's all we need. It's going to be a queue here. And then we are going to define our resource. So we have the arrivals, we have the queue. Now the resource, this machine. And as I explained already, we need 3 blocks to define this resource. We need a cease, we need a delay, and a release. So let's click on the first one, cease. Here we're going to add a resource. Again, we are going to select machine 1 because we already defined the name of the resource here in the experimental frame. And this number of units, I don't want you to get confused. Okay, so listen to what I'm going to say now. When you're defining the machine in the sys block, you click add, it's going to ask you for the resource ID and the number of units, but this represent is the number of parts that are needed for you to seize this machine. Okay, can you seize this machine with 1 unit? Then you're gonna just leave 1 there. If you need 2 parts to seize this machine, then you need to put a 2 there. If you need 3 parts to seize this machine, then you're gonna put a 3 there. This is not representing the number of machines. It's not representing the number of machines. This is representing the number of units, the number of entities that are needed for you to seize this machine. Like for example, sometimes you need 3 parts to do the processing in the machine. Sometimes you need 5. So unless you get 5, you cannot get started with the processing. So that will basically put the parts on hold. It will not seize the machine until you get all the 5 parts that you need to actually process the parts in the machine. Okay, so number of units is telling you the number of parts that are needed to seize the machine. If you want to change the number of machines, you have to come here to the experimental frame and change the capacity. If you want to have 3 machines, then you change this to 3. Okay, so the capacity change is here in the experimental frame. In the sys block, you're just defining the name of the resource and the number of entities that are needed to seize that resource. Okay, in the delay, we're gonna define the duration. Okay, so based on our model, the duration is given by a triangular distribution. So I'm going to copy this. And that will go here into the duration. Easiest way, again, you can just right click, build expression, go to random distribution, find the triangular. It's gonna ask you for the minimum, 3.2, the most likely, 4.2, and the maximum value, 5.2. And then click OK, and it will create the expression for you. And click OK. Then we get to the release block. So after you process the parts, you're gonna release. Which resource are you gonna be releasing? The same machine. And this is telling you the same thing. How many parts do you need to release the machine? We're gonna keep it in one, okay? After you're done processing one part, you can release the machine. Okay. Last thing we need to do is to count how many parts are being processed. Okay, so I'm gonna go here to the blocks and find a count block. And I'm going to use the counter ID that I defined, parts completed. And you see here, counter increment. So if you want to increment the counter just by 1, that's the default. But if you want to increase this by 2, every time a part crosses this block, then you have to change this to 2. And then finally, since this is the last piece of the model, we dispose. So the dispose block is going to destroy the entities so they don't occupy space in the memory. Any questions so far? Okay, so let's save this. And then we can check if we have any errors. Let's see. If you go to the Run tab, you can click here, check model. And if you get the message that I just got, no errors or warnings in the model, then you're good. If you got something else, let me know. Okay, so it looks like everybody's doing well. So in here, we're gonna go to setup. This is asking us to know how many units are produced in 8 hours. Okay, so we're gonna run this we're gonna go to replication parameters. We're gonna run this for 1 replication, but the replication length is gonna be 8 hours. And the other important thing is to change the base time units to minutes. Why is that? Because everything that we define in the model, the iterable times, the processing time, are in minutes. So the base time units of what we inputted into the blocks is minutes. Replication length, we can put 8 or we can put 480 minutes. It will do the same thing. In the reports, remember to select the Simon summary report and then click OK. And let's see if this works. So if you did everything, you run the model, you should have parts completed 105 in 8 hours. Anybody getting something else, something different? Questions, comments? Say something.
Everything went good on my end.
Okay, thank you.
Professor, do we have to submit the file now, or it will give some time to work on this?
Oh, so you don't have to submit this file. The file that you will have to work on, if you go to here, to modules, this is the assignment, and this is due on Monday next week. Okay, so in the assignment, you have a similar model with the difference that instead of having just one machine, you have three or three different type of machines. And each one of them has a different capacity. So for the drilling station, it follows a uniform distribution and you have 2 drills. For the mill machine, you have 3 mills, and that follows a triangular distribution. And for the grinders, you have 2, and this follows a discrete random variable defined as 25% of the jobs takes 6 minutes, 50% takes 8 minutes, and 25 requires 12 minutes. So how do you define that? A discrete distribution is defined as follows. So let me take this.
Professor, I'm having an error while running the simulation.
You have an error?
Yeah, it's showing this module has not been edited. This kind of error.
Okay, 1 second.
Okay.
Can you share your screen?
It's disabled. I think you
Okay.
disabled it. Yeah.
Okay, so this is Fantasia, right?
Yep.
Can you try it now?
Yep. So far, this is the module actually, but the interface is completely different than yours. Can you see it? Is it clear?
Yeah, I can see it.
Yeah.
Can you run it?
This is the run button, I think. Yeah.
Mhm.
This module has
Okay,
not been edited.
Can you click find at the bottom?
Yep. Here is the button.
Okay, the queue. So go to the queue,
Which one?
double click,
This one?
double click, yes. In the queue ID, you have to select.
Machine queue?
Actually, if you just click on that arrow, it would show up machine queue, yes. And click OK,
Okay. So do I need to run it again?
yes.
Okay. So where is the result?
click stop again and run it again.
Mm,
You have the stop button.
Where is this stop button?
That's the play button, and then on the other side is the stop, the square, the black square.
Okay.
Yeah.
I
And
would
then
save if possible too, just in case.
Yeah, sure. Yeah, it's running, I think.
Okay, stop. There you go. Yeah, I think you didn't define the something is wrong. Can you stop?
Where is the main file?
Go to run at the top. The run tab.
Okay, run tab. Sorry.
Yes. Setup. Go to reports. Go click there and select the last one on the category. In the default report, there's an arrow. Select the assignment summary report at the bottom. Okay. Go to replication parameters at the top. Click OK and run it again.
This replication link, it was 480 hours too, instead of.
Okay. Go back to run. Setup. You can change the time to minutes.
This one?
Yes.
And this time is minutes or hour?
Minutes.
Okay.
And run it again.
I don't know how to close it.
Gonna have to close that report.
Where is the close option? I don't find anything.
Can you stop? Yes. Close that.
It's not working. I mean, where is the main file?
Can you use the stop button at the top?
Yep.
And then see if you can close the crystal report.
I don't find anything.
What if, can you save? Just click save and then close. Use
I can open the file. Where is the file? This is the file.
Okay. Now run it.
Let me check if everything is okay. Yep. Yeah. Is it okay? The result.
Where's the notepad?
Yeah, this is the notepad.
I cannot see it. I'm seeing just the.
Okay.
You're sharing the arena.
Yeah, I think right now it's available. Can you see it?
Yeah, can you scroll down? Yeah, those are the results. Okay, parts completed 105. Good.
Okay, thank you. Yeah.
Okay.
Thank you, Professor.
No problem. So I was going to explain how to define these 25% of the jobs take 5 minutes, 6 minutes, 50% 8 minutes, and 25% requires 12 minutes. So in Arena, there's one of the distributions. Like let's just pick a delay here. If you want to build something like that, you go to build expression, the random distribution. The one that you're gonna use is called discrete probability. And these are cumulative probabilities and values. So you start with the probability and then the value, then the next probability, then the value, and so on. In this case, you have 25% of the jobs take 6 minutes. So how do you enter that? It is 25% take 6 minutes. Okay, and then we move to the next one. 50% requires 8 minutes. But since this is cumulative, the probability is going to be entered as 0.25 plus 50%. So that will be 0.75. And this will be 8 minutes. And then the last one is 25% requires 12 minutes. So 75% times 0.25 is 1. And then that requires 10 minutes. So to define the discrete probability, you have to use first probability of the first one, 0.25, and the value associated with that, 6 minutes. Then the second probability, but the probabilities are defined cumulative. So that means that you have to add that 50% to the previous probability, which was 0.25. So that will be 0.75, 8 minutes. And then the last part will be 25%. So 25% plus 0.75 is 1. So 100%. And that third part will require 10 minutes. Okay, so that's how you define a discrete probability distribution. And I'm gonna make this video available in case you have questions or you wanna go back to this. You go towards the end of the video, you can check this, how to define that discrete probability. The other thing, invalid expression.
The first parenthesis.
Okay. Okay. The other thing that I want to discuss here is that the queues have a capacity now. So drill queue can hold up 2 jobs at a time. Mill queue can hold up 3 jobs at a time. And grinder can hold up 2 jobs at a time. So what that is doing is basically stating that your queues have capacity, right? So for example, that first queue has a capacity of 2. So meaning that you can only put 2 parts there and the rest of them will not fit into the queue. So what's gonna happen is by zooming here, if I make that queue capacity 2, the parts that are going to arrive after I have 2 in queue are going to be discarded. I want to know where those go, right? So if I go to view, and I zoom here, you'll see that the queue have 2 outputs. This is the normal output, and this is the output for discarded parts. So if I put a capacity of 2, and I get another part coming in into this queue block, I can dispose those by using this second output. But what I want you to do in this lab is to count the number of parts that are being that are ejected because the queues are full. So essentially, what you're going to do is you're going to put a counter here to count how many parts are going to be discarded because they don't fit in the queue. And you will do that for each one of the stations. Okay, and that's the assignment that you're going to be submitting next week. My advice is that you go over that assignment tomorrow, check it out, and if you have questions, we can talk about 5 minutes on Wednesday. If you have specific questions, we can address those on Wednesday. before we get started with the next lecture. Okay, so I think I used all my time. Any questions? So if there's no questions, I'm going to stop. Yes,
Professor, we will get the recordings today.
yes, yes. I will put them in the modules. I will put the link in the modules.
Thank you, Professor.
Any other question? No? Well, if not, then I'll stop now and I will talk to you on Wednesday. Palaniapan, can you stay for a minute?
Yes, sir.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you.
Thank you, Professor. And I have a question for the arena this application. Hi, Professor.
Yes, for what you said?
Yeah, for this arena software.
You have a question about the example that we did today?
Not the sample. I'm trying to download this software, and I changed the email address because I just waiting for the text state. I tapped the text state email last day, but it's not working. I didn't waiting. Oh, I didn't get any email.
It will get to your junk mail. You have to go to the junk mail.
Yeah, I used another one and I got the email, but when I download it, I found it's only served for Windows, right?
Oh, and you have an Apple computer?
Yes.
Oh, I see.
Yeah, is there any download can serve for the iOS system?
I don't think so. So
Okay.
the other option is to try to work in the, I don't know if Dr. Dong has a computer in the lab
Okay.
that she can give you access to her lab and then you can work from there.
All right. Okay, I understand. Okay,
Yeah.
I figure out to get a Windows system.
Yes, yes.
Okay. All right. Yeah, that's just a one question for me.
Okay. Sorry about that.
Doesn't matter. I just to ask, is there any other link to serve iOS download? Yeah.
Okay.
If not, I will figure out to get a Windows system. Yeah.
Okay.
All right.
Good.
Thank you so much.
Thank you.
And have a good day.
You too.
See you
Bye-bye.
on Wednesday. Yeah.
Yes. So
Yes, sir.
So I wanted to check with you on the poster. I know you sent me the
Yeah.
latest one.
Yes.
I think we need to use the results from the simulation paper that I published because I don't think we got strong results
Okay.
for the simulation experimentation that we did. I think we need to do more on that side. So, but since we are running out of time, I think you can use some of the graphs that were in the presentation that I shared with you.
Okay.
So can you include those into the
Yes, yeah.
poster and then update that and send it to me?
Yes, I'll just do it now.
Okay.
Yes.
Yeah. So we'll talk. So you say it is due on Friday, right?
Yes, sir. Coming Friday. Yeah.
Okay, good. So we'll still have time. Okay.
Okay.
Good. That was it.
Yeah. It's good. I'm doing that.
Okay. So let me know when you had it ready and
Yes. Yeah.
send it to me.
Yes, sir.
Okay.
I will just send it to you. Yes.
Okay. All right.
Yeah. Yeah. Thank you, sir.